All right, ladies, gentlemen, and beyond. It is almost Halloween. Happy Spooktober. Who's excited? Before we move on and begin talking about chemical bonds, how atoms join together to form new substances called chemical compounds, I do want to just mention one thing real quick about the content that we discussed last time. So far, you should be able to look at the periodic table of the elements. You should be able to know what type of element we're looking at. Is it a metal or a nonmetal? For example, calcium here, it's on the left side of the table in group 2. I know it's a metal. Sulfur over here, it's on the right side of the table in group 16. I know it is a nonmetal. Not only that, you should also be able to look at an element, look at a main group element. Remember, the main group is the first two groups over here, and then this block over here. We ignore these guys in the middle, the transition metals, because they're kind of funky. Any main group element, you must be able to look at it and tell me how many valence electrons that element has and in what energy level those electrons reside. Hopefully you remember that electrons exist in different energy levels around the nucleus of the atom. And the outermost energy level we call the valence level, or the valence shell. And the number of electrons there in the outermost level we would refer to as valence electrons. Sodium, for example, has one valence electron in the third energy level. I know that right away, very simply, because it's in group 1, one valence electron. It's in the third period, the third row of the table. One valence electron in the third energy level. Chlorine, over here, has 7 valence electrons. It's in group 17. And its 7 valence electrons are also in the third energy level, period 3. What I'd like to draw your attention to now is this idea that the number of valence electrons greatly impacts and influences the chemical properties of the element, how that element reacts with other stuff to form new substances, to form chemical compounds. You guys already know that often elements will seek to change their number of electrons to form ions. Sodium here will lose that one outer valence electron, and right underneath it has 8 valence electrons, just like neon. That's called an octet, and therefore sodium becomes stable by losing that one electron and forming a 1 plus cation. What I would like for you to know now is that the closer an element is to forming an octet, the more reactive it is, the more desire, the more motivation, so to speak, it has to do so. Sodium only has one valence electron. All it has to do is get rid of that one valence electron, and right underneath it has an octet, just like neon, which is very stable. So sodium is so close to becoming stable, to becoming like one of the cool kids, one of the noble gases, that it is very excited and very ready to do so. Same thing with chlorine. Chlorine likes to gain a single electron. It has 7 valence electrons. It wants to gain one to become like argon, to become a cool kid. So anything that is very close to doing that, to having an octet, the closer the element is to having an octet, the more reactive it is. So the first two groups are quite reactive. Group 17, very reactive. Group 16, pretty reactive. And then the further you get into the middle of the table, the less reactive the elements are, the less motivated they are, the less excited they are to change up their electrons. Just something to think about. That's what I'm saying right here. All right, enough review. Let's get down to business for today. Today I want to begin discussing chemical bonds. A chemical bond is a strong attractive force between atoms, holding the atoms together to form a brand new substance called a chemical compound. Chemical bonds are not broken by ordinary means. You need to know that chemical bonds are, technically speaking, electrostatic forces. What does it mean to be an electrostatic force? What is that? Another term for it, which I mentioned down here, is Coulombic force, force of attraction. Hopefully you remember this. These are attractive forces that follow Coulomb's law. Charged particles, positively charged particle, negatively charged particle. There's a force of attraction that they have towards each other. You no longer need to know Coulomb's law, but it might be helpful here to remember that the force of attraction is directly proportional to the size of the charge, how big the charge on the particle is, and inversely proportional to how far apart they are, to the square of the distance between them. Chemical bonds are just electrostatic Coulombic attractive forces between atoms, holding those atoms together to form a chemical compound. Chemical bonds are not easily broken. Now let me remind you, this is different than those attractive forces we were looking at earlier this year that occur between compounds. Let's look at this slide. This is a chemical compound. How do I know that? Because it is formed from two elements, hydrogen and chlorine, and they are stuck together via a strong chemical bond. Here's another chemical compound, hydrogen and chlorine, stuck together with a strong chemical bond. This is a compound. We were analyzing earlier the phases of matter. If matter is a solid, a liquid, a gas at room temperature, how those phases can change. And hopefully you remember what this guy right here, this dotted line represents. We call that an intermolecular attraction or intermolecular force, an IMF, right? That is an attractive force between compounds, between molecules. The atoms within the molecule are held together with strong chemical bonds. That is what we are talking about now. We are no longer looking at the attractive force between molecules. This intermolecular force is easily broken. If I add heat energy to the system, I cause the particles to move more and more rapidly. Eventually, what's going to happen to this intermolecular force? It can break, and the particles can fly apart from each other in the gas phase, correct? Those intermolecular forces have to do with the phases of matter. It is like now we are zooming in, no longer worrying about what's happening in between molecules, how the phase of matter is affected, but we are looking at what is happening within a molecule, what's happening when atoms come together to form attractive forces. This is a strong chemical bond. This cannot be broken by ordinary means. This cannot be broken simply by putting a pot of water on your stove and boiling it. The one here represents what? Intermolecular forces. Yes, that is easily broken. You can break that by adding heat energy, putting a pan of water on your stove, heat it up to a boil, convert it from a liquid to a gas, break the intermolecular forces, liberate the molecules into the gas phase. We're no longer looking at that. We are now zooming into the molecule itself and asking, what is holding these atoms together? Hydrogen to oxygen to hydrogen. What does this represent? How do those chemical bonds work? What makes them so strong? Why do atoms form chemical bonds at all? That's what we're looking at. These chemical bonds, they can be broken, but not by easy, ordinary means. You cannot put water molecules on your stovetop and expect for the hydrogens to be broken apart from the oxygen. Chemical bonds are not easily broken. So we're talking about these attractive forces, these Coulombic electrostatic attractive forces between atoms that hold those atoms together to form compounds. Why do chemical bonds form at all? This is a rule that you guys have heard over and over again. Systems in nature always seek the lowest possible potential energy configuration. You already know that individual atoms like to gain or lose electrons to achieve an octet. That's what we were discussing earlier. Sodium will lose one electron. Chlorine will gain one electron. Why? Because the octet, having 8 valence electrons, like the noble gases, just so happens to be a very stable, low potential energy arrangement for the atom. Systems in nature always seek the lowest possible potential energy configuration. So let's imagine this. Let's imagine that we have 2 atoms. Maybe they are hydrogen. And those hydrogen atoms are getting closer and closer together. So you can see here on my graph, the x-axis represents how far apart they are, what we call the internuclear radius, or the internuclear distance, R, the distance between the particles. As the particles get closer and closer together, at some point the potential energy of the system reaches a minimum. If we were to shove the particles even closer, now they would be too close, and their nuclei would start repelling each other. Do you remember what is in the middle of every atom? Yeah, the middle of every atom has a positively charged nucleus, correct? If we get the positively charged nuclei of two atoms too close together, they will start to repel each other, and that is very unstable. The amount of potential energy skyrockets at that point. So there is one point, there is one distance between atoms where the potential energy is the lowest, and the system will always seek that lowest potential energy arrangement. It's the most stable arrangement. And what is keeping these atoms together? It is the fact that the potential energy has reached a minimum. Systems in nature always seek a potential energy minimum. And it is electrostatic forces between atoms. Let's zoom in here and see what's really happening between these two atoms. We know that atoms are composed of what? Subatomic particles, yes? The ones in the middle, the protons in the nucleus, have a positive charge. But what do the atoms have zooming around in energy levels, forming a cloud on the outside? That's correct, they have electrons, which are negatively charged. So this is what we would see. The negatively charged electrons of this atom are going to attract to the positively charged nucleus of this atom. The negatively charged electrons of this atom are going to attract to the positively charged nucleus of this one. So we have attractive forces. And the attractive forces are the strongest and the most effective at a certain distance. And that distance just so happens to be the point at which the potential energy of the system is at a minimum. Atoms bond together. Instead of remaining isolated in nature, they bond together because nature always seeks its systems to have the lowest potential energy state. And when atoms are bound together, when they're attracted to each other, the electrons of one atom attracted to the nucleus of the other, and vice versa, then the system can indeed reach the lowest possible potential energy state. So that is why chemical bonds form. So we can think about it in terms of energy, reaching the lowest possible potential energy, and we can think about it in terms of attractive forces between atoms.